Confidence intervals for proportions. Part 2. If we are going to do a problem by StatCrunch, we still have to check the conditions before we begin. Condition 1, we need to make sure np hat times the quantity 1 minus p hat is at least 10, and that the samples are independent by making a statement that we can reasonably assume population size n is at least 20 times that of the sample size. Example. In a random sample, 136 of 400 people given a flu shot experienced some discomfort. Using StatCrunch, construct a 95% confidence interval for the true proportion. We start by checking the first condition. np hat times the quantity 1 minus p hat is greater than or equal to 10. P hat is equal to x divided by n, or the number of successes divided by the sample size. We have 136 for the x, and the sample size is 400. This gives us 0.340 for the p hat. N is 400. So I'm going to plug in all of the values into the equation. 400 times p hat times 1 minus p hat gives us a value of 89.76, and that is clearly greater than or equal to 10. So the first condition is met. The second condition, we need to make a statement. The sample is less than 5% of the population. The population size is assumed to be greater than 400 times 20, or 8,000 individuals. Since both of our conditions are met, we can start the problem. I'm going to go to Stat, Proportion Stats, one sample with summary. Stats, Proportion Stats, one sample with summary. The number of successes is 136. The number of observations is the sample size, so 400. Click confidence interval, and we want to do a 95% confidence interval, so we'll set it at 95 and press compute. And here is our StatCrunch output. We have our confidence interval given as the lower limit and the upper limit. Thus, we are 95% confident that the proportion of people who will experience some discomfort after receiving a flu shot is between 0.294 and 0.386. The margin of error for a proportion is defined as E equals Z times the square root of p hat times the quantity 1 minus p hat divided by n. If I were to solve for n, I get the equation n equals p hat times the quantity 1 minus p hat times the quantity z over e quantity squared. Now, if p hat is given in a problem, then use the p hat that's given. However, if p hat is unknown or cannot be determined, then we want to use p hat equals 0.5. The reason we want to use p hat equals 0.5 if p hat is unknown is it actually maximizes the sample size. It maximizes n, which gives us a more conservative approach to the problem. Example. Using the info from the previous problem, determine the minimum sample size needed if you wanted to be 95% confident and yet only have a margin of error of 2.5%. Do this with p hat equals 0.5 as well. In the first problem, we use the fact that p hat equals 0.34 based upon our original sample data. In the second column, we are assuming that we have no prior knowledge concerning p hat. So we're going to do the problem twice. One from a prior estimate. From the previous problem, we know that p hat is 0.34. And the formula for the sample size is n equals p hat times the quantity 1 minus p hat times the quantity z over e squared. Let's plug in the values. 0.34 times 1 minus 0.34 times z. Z is 1.96, and we'll use our t-table to find that number. E is the margin of error. In this case, E is 0.025 because we converted 2.5% to a decimal. So that's our E value. And we have to square the expression. This gives us 1,379.3, and that rounds to 1,380. Now I intentionally rounded to the nearest whole number, which gives me 1,380. Although this number on the right side is less than 5, we always round up, because this is the minimum sample size we need, so we have to include the full person up. So always round up for sample size. On the other side, let's assume we have no prior estimate, so we're going to use 0.5 as our p hat. Again, the formula is n equals p hat times the quantity 1 minus p hat times z over e squared. We'll plug in the numbers again, 0.5 this time because we're assuming we have no prior estimate. 1 minus 0.5 times e, which is still the same, 1.96, divided the margin of error, 0.025, and then we'll square this number. This gives us 1,536.64, and that rounds to 1,537. Again, I always want to round up, so I have the minimum sample size that I need is 1,537 individuals. Example: a school administrator is concerned about the amount of credit card debt that college students have. She wishes to conduct a poll to estimate the percentage of full-time college students who have credit card debt of $2,000 or more. How big of a sample will she need if she wants to be 95% confident and only have a margin of error of 3%? Since p hat is unknown in the problem, we're going to use p hat equals 0.5. And I want to have a confidence interval of 95%, so we need to use z equals 1.96. E is equal to 3%, so in a decimal that's 0.03. And we'll plug in the values into the formula. N equals p hat times the quantity 1 minus p hat times z divided by e quantity squared. P hat is 0.5 because we do not know what the prior estimate was, so we'll use 0.5. and z is 1.96 divided by 0.03, the margin of error, and we'll square the expression. This reduces to 1067.11, and we are going to round this to 1068. Remember, we always round up because this is the minimum sample size we need, so we need to make sure we have at least the minimum.